Yes.
May I ask Group B and your result 2, the slide, what's the y-axis and the x-axis and the physical meaning? Would you please show us the result 2? Yeah, what's the x-axis and the y-axis? What's the meaning?
Oh, this is the x-axis is the length and the y is the decay, the annihilation ratios.
Length of the tube.
Yeah, this one is the length of the tube.
So the y is the delay, the time of the. I can not really understand the unit. What's the unit?
It looks like MMS.
Minutes.
Minutes.
MMS.
Minutes.
Yeah.
Is that right?
MMS.
Or is that millimeters per second?
Yeah, I don't know. Yeah, maybe meters over millisecond or millisecond or I don't know.
Millisecond.
Millisecond. Okay. Yeah. Thank you.
I think teachers or students can ask or clarify something. Yeah.
So to Group B, so did you actually get like theoretical results? Like from your theory, did you get a number like how fast it should move in the pipe or something like that? And yeah, did you compare it to your experimental results and did they match?
Yeah, they do match because we found because there's a formula that F equals mu s times n. So we found that aluminum's the coefficient friction of the aluminum is much bigger, not much bigger, but bigger than copper's. So actually, the friction along the aluminum pipes wall have to be bigger than copper, and that's why it will decay more strongly.
So that matched the theory that
Yeah.
we.
Sorry, maybe I misunderstand your slide because I think so. You mean the length will affect the velocity delay, or
This is like when the length is 10 centimeters, the three materials will go like this. The aluminum, the annihilation ratio is the aluminum is bigger than the steel and bigger than the copper. And this one is in 15 centimeters. The ratio is aluminum bigger than steel and bigger than copper. And this is an accidental.
Sorry, so how can you define your attenuation ratio? What's attenuation ratio? Means the time delay or the velocity after your calculation, so you can compare with.
We did the calculation to find out that the time when is like the calculation is things that we did the calculation and about the time, so we can see that we have like A speed, B speed, C speed in aluminum, and we will use B to minus A.
Yeah. Okay. So I think I can understand you. So can you show me your C equals the bulk modulus would you please show the slide? Yeah. The velocity of the C equals root. You know you.
C means basically all sound wave.
Sound wave.
Slide.
Yeah.
You had a slide.
Yeah, so can you tell me what's the difference between in my opinion, this is the air velocity of the sound, but what's different from the copper and the material will affect which one? Or you mean, maybe I don't know what you're going to show us. So you mean the equation is affected by the material?
Oh,
C means the velocity of sound wave. But we think according to this changing delay of quality also changes too. We think.
Yeah, so I feel confused about the topic is you have to measure the sound in the tube by the air through the tube, the velocity, or you mean the sound just transferred by the material?
We can measure the delay of quality from oscilloscope, but we couldn't measure the velocity. Yes.
Okay, so would you please tell me what's your device? How did you make your device?
Device?
Yeah, you measure the velocity through the air or through the material? Yeah, I know, but yeah, because the tube, if you measure the sound goes through by the air and goes through by the material, that's totally different.
Yes.
I want to make sure which one you measured.
Low.
Because they say that the material did not affect a lot, but your data shows that does affect, right?
Right. Oh yes. Changing the materials. Also, the wave shapes are clearly changing. So we think the changing materials is the important keyword of about the quality of sound wave.
Yeah. So you mean the material you change the wave shape, right? Wave shape or
Two. Wave shape too, and not wave shape, but
or the velocity, the
Yeah.
viscosity. Or at first you show us the viscosity and the radon number or something. Is the material affect the viscosity or the radon number?
yes.
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 Okay. So how about you? Do you think you say that the material doesn't affect the velocity? And what's your opinion about the explanation, or do you have any explanation for your results?
Excuse me, I would like to do a small explanation. Is that this pipe is hollow, so outside the pipe is like aluminum or it has different materials, but inside is the hollow. So the sound speed still go through the air, but it will has friction between the air and the pipe.
Material. Yeah,
Yeah.
no, yeah, that's good. Yeah. So I understand your experience. So you really you the same. You measure the sound wave from transferred by the air,
Yeah.
but the material will affect the viscosity.
Yeah.
Yeah, I think that makes sense. Yeah, okay. And how about your explanation or your thought?
So the two main things that we focused on was the frequency, because if the frequency, so if we think that the frequency and the inner radius is what affects it, we didn't really talk about the material, but I don't know.
Maybe you have some ideas, right? I mean, students in your group.
In our idea, and the viscosity affects the speed of sound in a thin tube, because in our formula there is the value of viscosity, so I think the viscosity affects the speed of sound, I think.
So more than the material, it's the diameter and of the tube.
Yeah.
More than the material. Material is not so important.
As much as.
Not as much. Okay. That was kind of your question.
Yeah. Good.
Okay, we have a few more minutes. You have other question?
Teacher first.
No, you raise your hand first.
Thank you very much. Group A and Group B, both of you, thank you very much for a good presentation. I'm a teacher of mathematics, so I'm interested in formula. I'm very interested because each group use different formula. One group A used formula made by Helmholtz. I heard Helmholtz as thermodynamics, excuse me. And on the other hand, Reynolds number group B use. I heard the name of Reynolds as fluid dynamics. So each groups use different formula and different method. I'd like to, I want to know the reason why you choose each method or formula.
Why don't you start? Both groups can answer. You want to start?
I think we probably use different perspectives to measure or to calculate the sound of the velocity of the sound. In our group, we use thermodynamics, and in other groups, I think they can use force or other elements to measure the velocity of the field.
Okay. How about the other group? Yeah.
I also read Helmholtz's book, but it is so difficult, and I found the formula. I think so very complicated. So I decided I can't understand that formula. So I made another book. It's so easy. So it says, if you are a monkey, you can understand. That's what it says. So I did, and that so easy formula. It is also atomic velocity formula. That's so common. So I use a common formula.
Thank you very much.
Okay, thank you, and an excellent question and answers.
You want to add something?
The reason we select it, the method is we think that method is very simple, and we can watch the wave by the oscilloscope clearly. So we selected that method.
Thank you very much.
Did you want to add a little bit more? Yeah.
Do you want to add or do you want to ask?
Ask.
You want to ask?
I want to group B. Why do you use real number into your PowerPoint, but not really calculate it just from the theory?
Can you repeat your question again?
Why do you put real number into your PowerPoint, but not really calculate the velocity of the sound just by the theory?
You mean we didn't calculate the sound by the
Just
Reynolds
theory.
number?
Yes, you don't use real number into
Well,
your
Reynolds number is it's already calculated by other people, so we can find the information on the internet. There's no need to use it, but we only need to see the relationship, so we can choose the factor we want to change.
I mean is that you don't use real number into your formula, but why do you measure it?
Did you use the constant number in calculating?
You can probably claim it is a constant number, but you don't put it in your formula. It's the point.
number is one of the background to understand the fluid. It's the basic knowledge to understand the fluid, how it flows, or how we can see the decay. It's the basic information. We didn't have to use it, but we have to know it first before we did this experiment.
So you can claim that the number is useless for this experiment.
It's not that useless because when we can see that the Reynolds number we can identify the flow we want to see, so we can choose whether the sound speed. So we can see that if the sound speed is higher and it is the turbulent flow, so the decays will be smaller. It will become smaller. So we still use it.
All right, thank you very much.
Thank you. Yeah, I think studying Reynolds is what helped you to set up your experiment. Studying what Reynolds did and reading the book that even a monkey can understand, that's what helped you to set up your experiment. And you had also a very good question.
Yeah, may I add some information for the group B, because I think their explanation is good for me, because but I think is that the common? Did you comment? Sorry. Yeah, it's okay. Because I think that both team is very good at the experiment and the research, but the emphasis on different part, because they focus on the radius of the tube. Okay, I think they can get good experimental data and the theoretical calculation. But at Group B, they just focus on the material. Yeah, but since they think the material is not really affect, but still affect, right? So they just ignore the difference between different materials. And Group B, they do the different material, and we can see, in fact, that is not really big difference, but still affect the velocity in the tube. And I think I want to answer the question of the boy. Yeah, because the viscosity is difficult for us to measure in high school lab, because we try to buy the machine is about 1 million, more than 1 million. I think the good one is the cheap one, maybe 200,000 or 300,000. So we cannot really get the real number. But if you can really measure the real number and the viscosity, we can do much more research on or calculation on the fluid mechanics. Yeah, and that's all. Thank you.
Okay, great, thank you. I think we have some comments from 2 teachers now also about theme 2. I'm not sure who's going first. Okay. Yes.
Thank you very much for your nice presentation. I think this collaboration is going very well, and I think there are some tips to carry out this experiment. One is how to make sound go through the thin tube. I think it is very hard to go through. And the second is how to measure the time. In Japan, we use the oscilloscope. However, in Taiwan, they use the very simple computer software. It's very good, I think. And third, the selecting a good sound is very important, because the sine wave is sometimes not for measuring, because the shape is very complicated. And I think you cleared this point. And could you tell me how you clear that point? For example, selecting the sound and measuring the time, and making the sound go through the thin tube.
That's a question for both groups, right? Okay. Both of you can answer.
For the sound, we need loud sound to go through the tube. So we use 2 microphones and the sound stick, and so we can this machine can know the waves when the waves comes and the wave shape.
What is this machine?
Just add the same one, but the same powerful machine, 2 things. And it can know the wave shape and when the wave come, and so we will find 2 waves, and we will know the time between the 2 waves begin, so we can know the time.
Automatically?
Yes, automatically. And you will know the shape, but because the time is very small, so we need to zoom in and zoom in to know where the. So we can get and so by this machine we can get the similar graph that which is similar to the graph we get from Audacity or the software you use, and we also need to calculate it by ourselves to calculate the velocity of speed, and just in the same way to find the different time which when 2 different waves came out, and try to find the difference between the time, and we calculate it, and we use the depth of tube to we use this time to divide the depth of tube, so we can get the velocity which runs through the tube.
How about the other group? How did you measure the time?
Just like the teacher said, and in Taiwan we did the experiments by some errors. So like Japan students, they have correct our error, because when they did the experiments, they even put the tape over the aluminum pipe or something like that. So make sure it is tight to the earphone. So we can know that the sound will go travel through the pipe, not the air outside.
Go ahead.
Thank you. Sorry, in fact I already commented before, but I think this I want to tell everybody. I think this is very amazing for me to see 2 groups did a great job of this topic, because that topic is very difficult for high school students, because the background knowledge is totally did not teach in high school, and you can both get the good paper research and know by yourself to study the advanced courses for the research. I think this is very important purpose. We encourage students to do the research by yourself, and you can learn by yourself. That you can do much more in the future. Yeah, that's all. Thank you.
Thank you very much. Yeah, I'm very, very, very much older than high school students. Very much older. But I do not understand the formulas that you used. But I think it's great that, yeah, as the teacher said, that you are going beyond what you have to do every day in school. And that's where our Japanese students and our Taiwanese students, you guys are pushing the limits, and that's why this is a really, really good project. We didn't learn that. What page is that on in the textbook? I don't know. So you guys really had to research and find it and try things, and I was very happy to see that. That's why this project is great. I'm an English teacher, so I'm going to ask you a quiz question right now, okay? Who said this? if I have seen further, it is because... Finish the statement for me. It is because...
I stand on the shoulders of giants.
It is because I have stood on the shoulders of giants. And your answer was Isaac Newton. Isaac Newton said this in a letter. Okay? If I have seen further, it is because I have stood on the shoulders of giants. Now you answered that, many students answered that very fast, so that was in the textbook. Maybe. Okay. Actually, you got the wrong answer. Oh my God. No, you're right. Isaac Newton said that in the 1600s, but if you get back on your favorite website, Wikipedia, you will see that that statement is even older. 12th century, okay? So almost 1,000 years ago, people were saying, oh, the giants came before us, the great people were before us. We stand on their shoulders and we can understand more, we can see further. So it's even older than Isaac Newton. But we still use that, and Newton is very famous for saying that about physics, about science. Okay, so what you're doing, I see this project, what you're doing is standing on some big shoulders. Helmholtz. I don't understand Helmholtz, but he did. His applications are everywhere. And Reynolds is everywhere. And the Lab Quest 2 magic machine that you use to measure waves and electricity, okay? Why don't you research the Lab Quest 2? Who made that? Whose research went into that? Right? It's not magic. It's not magic, yeah. It's a real product of real research from many people, probably many countries. So why don't you check the history of the Lab Quest 2? And you can make the Lab Quest 3. Maybe. So this project does have a lot of practical application and a lot of vision. You guys can keep going. It should be endless. Science is endless. It's great. I want to say one more thing. I was really, really happy and interested in watching the different groups working because Group A, in, for example, the train, simple train, Group A was more hands-on. You guys were, immediately we said, okay, ready, go. Leo said, okay, ready, start. And you guys started getting a coil and putting the magnet and the battery through the coil, and you tried the angle, and you were measuring the angle immediately. And Group B was doing a different approach. You had kind of a plan set out, and you were putting the data in, and you were checking what the Japanese team had done and the Taiwanese team. And eventually, it kind of comes together.